Hello, welcome to the live session for Structure, Form and Architecture, the Synergy. This is a course that has been, this is an NPTEL course and it's an NPTEL online course which is offered by Professor Shubhati Sadhukan. He's an assistant professor at IIT Roorkee and I am the course TA. I am Shreya Shukla I am doing currently PhD at IIT Roorkee. So today we will be doing week 4, assignment 4 and as the session has already started, we will wait for 5 minutes for people to join. In any case, we will start in 5 minutes. We will just wait for 5 minutes for people to join. We will be doing previous year questions. We do not do this year's questions in this live session. We only do previous year questions to get an idea of what kind of questions are there and to help practice students and to help students learn better. So we will only be doing previous year questions. We do not do this year's question in these live sessions. We will wait for 5 minutes and at 6:05 we will start with the session. So it's 6:05. We will start with the live session. Meanwhile, if anyone joins in the between, that's fine. But in case no one joins, this recording is still available for access later. So we'll start today's session. So this is the subject is structure, form, and architecture, the synergy. And I have discussed these 4 terms, what all these means and how they are related and other things in the first live session. So we will not be going there, we will move forward. So sorry, there is a mistake here, it's week 4. Yeah. So week 4, the syllabus that we have has been covered in the NPTEL course for week 4. 5 lectures were covered: structural typology, compressive structures, tensile structures, load-bearing structures, and temporary structures. So in structural typology, which was lecture 16, it was covered the different kinds of types of structures that exist. For example, solid, surface, skeletal, membrane, and hybrids. And then all the different kinds of structures that are under these categories were covered. So solid includes walls, arches, domes. Surface includes grids, shells, plates. Skeletal includes trusses, frames. Membranes include pneumatic structure, cable tinged structures, and hybrid structure are basically one or two of the above combined. Okay. And then each of these types of different structural typologies, they were explained and different examples were given. And then in the next lecture, which is lecture number 17, compressive structures, firstly it was talked about compression, how the load occurs on in compression and how it happens. And then it was talked about how masonry and concrete have good compressive strength. And then compressive structures from history. And then compressive structures like walls, arches, walls, buttresses, dome. All of these things were talked about in detail, and some examples from histories, compressive structures in histories were given, especially from the Greek Roman temples and Gothic cathedrals. These compressive structures were very common. So these points were covered. Then comes the next lecture, tensile structures. So in tensile structures, it was again talked about tensile tension first, and how load happens in tension, the pulling load and other things. And then different types of tensile structures were discussed in this, which were stayed, suspended, anti-clastic, pneumatic, trusses. And then example of each of these types were covered to help students understand it better. And then uses of tensile structure were covered, which were how can it be used in stadiums, in sports arenas, in parking, in bridges, in cantilevers, and other things. Then the next lecture was lecture 19, load-bearing structures. So in this, again, a little part was covered on the definition, what is a load-bearing structure, different kind of loads that occur in load-bearing structure, how the load-bearing structure is transferring the weight from through the walls to the foundation and then to the soil. And then different kinds of wall arrangements were discussed in this, like cellular, simple cross, double cross, complex, and others. Examples of load-bearing structures were given, and then examples from history of load-bearing structures were also given, for example like Colosseum and Taj Mahal and other things. Then advantages and disadvantages were discussed. And then the last lecture of week 4, temporary structures. So what are temporary structures? They're basically structures that are constructed to give support, or to give initial support, or to give support to something that has been falling. And then two types of temporary structures were discussed in detail: shoring and scaffolding. and then different types of shoring was discussed, different types of scaffolding were discussed. Different types of shoring include raking, flying, and dead shoring, and all of those things were discussed in detail along with the diagrams. And then scaffolding was discussed, bricklayers, masons, steel or tubular, needle, wooden, and all of those things were again discussed in details. Underpinning was also discussed, and all the different kinds of scaffoldings and shoring. There are different parts that are part of these both temporary structures, they were discussed. So this was the syllabus that was covered in week 4. Moving on, we will start with our previous year questions, and I'll again would like to mention it that these are only previous year questions. We do not do this year's question in this live session. We only do previous year questions to help students understand the course better. So the first question is, so the first question is, which of the following is true for plain cement concrete structure? Plain cement concrete, and the options are PCC is poor in compression and good in tension. PCC is good in compression but poor in tension. PCC is good both in compression and tension. PCC is poor both in compression and tension. So what is PCC? It's plain. It can be called plain concrete or plain cement concrete or PCC, and it is most commonly used for paving and flooring and other things. So PCC is made up of 3 basic components, which is water and aggregate like rock, sand and gravel, and Portland cement. Cement is usually in powder form and it acts as a binding agent when mixed with water and aggregates. And the different types of aggregate and the ratio of materials would give different types of cement with slightly different properties. And if you have studied in your structures course exam, you would have learned that different grades of concretes are available: M20, M15, M25. All these concretes, they have different compressive strengths, in which the number dictates the compressive strength of that concrete. And these different grades of concretes have different ratios of materials of water, aggregate and cement, and that's how the compressive strength varies. And then PCC is also a brittle material, and it has low tensile strain and high tensile compression capacities. So it is incredibly, PCC is very strong under compression and it is very weak under tension. It means that when on a solid unmoving surface, it is capable of withstanding huge amounts of weight. If it's on a solid and stable surface, it can withstand huge amounts of weight because compression is pressing it together, tension is pulling it together. Pulling and compression is pressing. So if compression is the pressing load, so when there is a huge amount of weight on it, it can still withstand it because it is good in compression. However, if there is some kind of load which is pushing it apart, pulling it apart and creating tension in it, it won't stand that. And when placed under tension, it is much weaker and can often crack and buckle. So when it is put under tension, it cracks or buckles. As you can see in this exam, how compression, the material is, it is of course changing shape a little, but no cracks are happening, while in tension cracks are happening in this example, that in this diagram that I have added, and which is why it makes it the perfect material for ground floor layers and providing a stable and even base for RCC to be built onto while limiting its use in larger construction projects. So it is not highly used in larger construction projects, but it is usually used over RCC as a protective layer and a stable layer, and it is used for flooring and other reasons. Another example to show different kinds of cracks happening in it. These are flexural cracks and diagonal shear cracks. Both are different kinds of cracks that happen because of tension in concrete? So the answer is it is good in compression and poor in tension. Next question. Uh, Name the following structural form. Name the following structural form: ribbed vault, barrel vault, groin vault, and Nubian vault. So this image has been given and you have to identify which kind of vault is this. Moving forward, so I'll explain first of all what both kinds of vaults, all four kinds of vaults, how they look and what their properties are, and then we will be able to answer this question. So what's a ribbed vault? So it's an architectural feature. It comprises of a framework of crossed or diagonal arched ribs or the skeletal of arches or ribs on which masonry can be laid to form a ceiling or a roof. So there are different arches which are connected diagonally, and they take the load of the masonry of the roof from above. So that's a rib vault. It has a skeleton kind of structure, as you can see in the figure right next to it. There is a diagonal arch rib or skeletal kind of system in this, and various variations of ribbed vault were used in Roman architecture, Byzantine architecture, Islamic architecture, Romanesque architecture, and especially Gothic architecture. What is a barrel vault? So a barrel vault, also known as a tunnel vault, wagon head vault, it's an architectural element formed by the extrusion of a single curve or an arch, you can say, along a given distance. So basically it's an arch which has been stretched, so it looks like a vault. It's an arch which has been pushed beyond. The curves are typically circular in shape and it lends a semi-cylindrical appearance to the total design. And this is how the barrel vault looks like. It's a semicircular arch which has been extended, so it forms like a vault. Next is the groin vault. So a groin vault or a groin vault is produced by the intersection at the right angles of two barrel vaults. Groin refers to the, so what happens in groin vault is, for example, we saw what is a barrel vault. Okay, so now this barrel vault, just a second. So now there are two barrel vaults that are intersecting, and when this intersection of two barrel vaults are formed, then as you can see the image on the right, this kind of intersection forms this kind of shape. So groin actually refers to the edge between the intersecting vaults, and sometimes the arches of groin vaults are pointed instead of round. So the arches of groin vault could be pointed or could be semicircular or round. So it doesn't matter that much. So groin vaults, so the arches are can be pointed or round in groin vaults, and the construction of groin vaults was exploited by the Romans first, but it was difficult to construct neatly because of the geometry of the cross groins, which are usually elliptical in cross section, and because of which actually the rib vault gained more it came into Gothic architecture, and it was easier to construct compared to groin vault. So that became more prominent in Gothic architecture, that's why. So a Nubian vault, it is not a very commonly used vault or a very commonly uh, used structure in most of the buildings throughout our history. So it is a type of curved surface forming a vaulted structure just like any other vault, but it is made with bricks and the mud brick structures, and this mud brick structure was revived by the Egyptian architect Hassan Fadi. Hassan Fadi was is a very famous architect. You can look up his work. So he revived this technology when he found this somewhere in some Egyptian temple, and then this technology is advocated as environmentally friendly and sustainable because it makes use of pure earth without the need of timber and other things. And one of the advantages of the Nubian vault is that it can be built without any support or shuttering. And the earth bricks are laid leaning at a slightly slope, against the gable walls in a lengthwise vault. So I hope you understand that, and I have also added figures to help you understand. So now our question was that name this structural form. So as you can very clearly see that this is a groin vault. Why? Because two barrel vaults are intersecting and they're forming this shape, and that's how groin vault happens. So this is groin vault. So our answer is groin vault. Coming to our next question, dome develops dash along its meridians, bending stresses, compressive stresses, tensile stresses, and both compressive and tensile stresses. So bending stress happens when you put a load on a structure and it bends. Compressive stress happens when you put a load on the structure and it buckles in between. Tensile stress happens when you pull the structure and it gets thin in the between. So these are the three kinds of stresses that are being talked about here. So moving forward, so what are domes? Domes are actually self-supporting structures, and they take the form of an arch distributing external loads around the sides and down to the foundations. They are tightly compacted by gravity, and any other external loads are carried by the compressive forces that develop internally. And the analysis of a shell or a dome is concerned with two kinds of stresses. Number one is the stress that acts in the meridional direction, which is basically any kind of dome will have meridians, different meridians, and different hoops, which are basically parallel to the circumference or to the base. So in these two parts, two kinds of stresses act. Meridional stresses act on the meridians, and the hoop stresses act in the parallel direction or on the hoops. So meridional forces and hoop forces are two things that are happening in a dome. So this next diagram explains that different kinds of forces that are happening in the hoops and the meridians, what type are they? So first is the arrow that marks the red. It shows meridional compressive forces. Meridional because it's acting on the meridian and it's compressive force. Then dark blue we see hoop compressive forces. So compressive forces are actually acting in two types. It is acting in both meridians and also on the hoops, the circumferences, different circumferences parallel to the base. Then the sky blue hoop tensile forces, they are tensile forces that are acting on the hoop. So they are hoop tensile forces. So the meridians only have compressive forces. The hoops, however, have tensile forces as well as compressive forces. And lastly, the green, it's green part, it's basically the vertical and lateral loads which are being transferred down ultimately from this dome. So our question was, the dome develops dash along its meridians. So it develops bending stress or compressive stress or tensile stress or both compressive and tensile stress. So our correct answer would be it develops it develops both compressive and tensile stresses. I think there is something I may have marked the answer incorrectly. I'll mark it correctly. I'm so sorry for the confusion. But yeah, the correct answer is both compressive and oh no, sorry, I'm getting confused. It is only asking what develops along the meridians. So along the meridians, we only have compressive forces. Along the hoops, we have both uh, compressive and tensile forces. So yes, the answer is compressive stresses. I'm so sorry for the confusion. So it's only asking about the meridians and not in total dome. If the answer had been ki dome, what kind of forces act in a dome, so then the answer would be both tensile and compressive. But it's asking only in meridians, so it will be compressive stresses. Even if it asked in its hoops, then it would again have been both compressive and tensile. But in the meridians, only compressive stresses are occurring, so that's why the answer is compressive stress. Fourth, excuse me. So the ability of a material to prevent structure against pulling load is referred as compression, tension, shear or torsion. So in the last lecture I had talked about all these kinds of forces and stresses in detail. I would just cover it in a gist right now for this question. So compression force or compressive force, it occurs when a physical force presses inwards on an object and it causes it to become compacted. So compression occurs when this is an object and you're putting force from both the sides and it is getting compacted. In this process, the relative position of atoms and molecules of the object change, and this change can be temporary or permanent depending on the type of material receiving the compressive force. For example, if it's a spring, it will retain back its shape. And for example, if you are hitting a steel block with a hammer, it is not going to change back its shape, it would be compressed. Then shear force, it's a force acting in a direction that's parallel to over the top of a surface or cross section of a body, like the pressure of airflow over an airplane wing. The word shear in the term is a reference to the fact that such a force can cut or shear through the surface or object under strain. So it's a parallel force on an object which makes it split from the middle or shear from the middle. A tension is described as the pulling force. It is transmitted axially by the means of a string, a rope, chain or a similar object, or by each end of a rod, a truss member, a similar 3D object. It might also be described as the action-reaction pair of forces acting at each end of said elements. So it's an action-reaction force when two forces are pulling apart on an object. That is tension. Then torsion, it's if a torsional load is applied to a material, it will create shear stress which induces torsional force. If this force is large enough, it can cause the material to twist, and this twisting force is called a torsional force. So some examples to show what is tensional stress, what is compression force, what is shear force, and the what is torsional force, and other examples to show it. This is a simpler diagram to show how different kinds of forces of these, how they impact any kind of structure or object. So in tension, it's a pulling load, so it gets thin in the middle. Compression, it gets compacted, so it gets thick in the middle. Shear makes the object shear or split. Torsion makes the object twist. Our question was that the ability of a material to prevent structure against pulling load is referred as. So our answer would be tension, because tension is the force that is happening with pulling load. Moving to the next question. The McCormick Palace in Illinois is an example of trussed tensile structure, pneumatic tensile structure, cable suspended tensile structure, or staged tensile structure. So first of all, what is McCormick Place and how it looks like? So this is an image of McCormick Place, and it is the largest convention center in North America. It Consists of four interconnected buildings and one indoor arena. It is near Lake Michigan, Illinois, US. The architect was Gene Summers. The owner of this building is Metropolitan Pier and Exposition Authority. It was opened in 1912 and the height of this building is 96 meters. So the question was that this building is which one of these following structures. So we will discuss about these four structures first to be able to answer that question. So a trussed tensile structure. So a truss is a structure that consists of members organized into connected triangles so that the overall assembly behaves as a single object. Trusses are mostly commonly used in bridges, roofs, and towers. A truss is made up of a web of triangles joined together to enable the even distribution of weight and the handling of changing tension and compression without bending and shearing. So I hope everybody is aware what a truss is, or you must have learned about it in your course. And even if you don't know, so truss is basically different members are joined together in triangles and in other shapes to form an assembly, and that assembly acts as a single object. And it takes a lot of it enables the even distribution of weight and handling of changing tension and compression without any kind of bending or shearing. What's a pneumatic tensile structure? So pneumatic structures are membrane structures comprised of the volume of inflated air. They are extremely lightweight structures, and existing internal pressure pre-stresses the enveloping membranes that are subjected to tension and counteracts the external loads. So the membranes usually consist of ETFE foils, and it is stabilized by the pressure of compressed air. These are basically air supported structures supported by internal air pressure, and a network of cables stiffens the fabric, and the assembly is supported by a rigid link at the end. Then cable suspended tensile structure. The main pillar acts as compression members, but the whole load is carried out by cables which are in tension. A suspended structure is a structure which is supported by cables coming from beams or trusses which sit atop a concrete center column. The design allows the walls, roof, and cantilever floors to be suspended entirely by cables and a central column, and cable suspended structures are very common in bridges. State tensile structure. So the whole mass of the roof and other things, they're supported with the stayed cables, and the tension members are supported by the compression members, but the major loads are carried out by the tensile members. So the compression members, these there are masts in this kind of structure, and then the tension members are supported by these compression members, but majorly the load is carried out by the tensile members. That's a stayed tensile structure. So the answer is McCormick Palace in Illinois is an example of stayed tensile structure, because it is very evident it's not pneumatic, it is not trussed, and it is not cable suspended, so it's stayed tensile structure. Which of the following is an example of cable suspended tensile structure? So we just learned what is a cable suspended tensile structure. And the four options are here: Signature Bridge, Delhi; Havra Bridge, Kolkata; Mahatma Gandhi Setu, Patna; Pamban Bridge, Mandapam. So these are the four bridges: Signature Bridge, Delhi; Havra Bridge, Pamban Bridge; Mahatma Gandhi Setu, Patna. And we just discussed what are cable suspended tensile structure, that how one column or one beam suspended structure is there, and then all of the cables and these pillars or these structures act as compression members, but the whole load is carried out by the cables which are in tension, and it allows the walls, roofs and cantilevered floors to be supported entirely by cables or a center column. So this is a cable suspended tensile structure, and if you go through back through the images and coming back to all four images, it's evident that Howrah Bridge and Pamban Bridge are trussed structures in these bridges, and Mahatma Gandhi Setu is a regular structure based on load bearing, and Signature Bridge is supported by cables. So the correct answer of this question would be Signature Bridge, Delhi. Coming to question number 7, which type of load bearing structure is shown below? So one image has been given, and four options have been given, which are cellular wall structure, single cross wall structure, double cross wall structure, complex wall structure, and it has been asked that which type of load bearing structure is the image that has been shown below. So we'll have to understand all these four kinds of wall structures to be able to answer this question. So first is cellular wall structure. So in a cellular wall structure, the external walls form the boundaries of the buildings, and the internal walls are used to divide the space. They are connected as shown in the figure on the right hand side to form a cellular wall arrangement. All the walls here are load bearing walls or structural walls. All of the walls are load bearing walls or structural walls. In this arrangement, many identical rooms are constructed as shown in the figure on the right. It is used for hotel or hostel room construction, and as shown in the figure, there are openings provided in the walls. So openings in load bearing walls affect the load carrying capacity of the wall. Hence, in this case of a load bearing structure, it is advised to provide fewer and smaller openings. Next is your double cross wall structure. So in this arrangement, a complex system of cross walls are set parallel to both the major axes is adopted. This helps to use maximum daylight in the structure as shown in the figure. So it is very similar to cross wall, but it's a little more complex than cross wall, and it is an example where a complex system of cross walls are set parallel to both the major axes. For example, in this direction also the cross wall structure is there, and in this direction also the cross wall structure is there in both the major axes. So that's why it's a double cross wall structure. Next is complex wall structure. So in this kind of arrangement, a combination of cellular and cross wall arrangements are followed to meet the purpose of creating various sized spaces within the building. So it's a combination of cellular and cross wall arrangement to fulfill the purpose of creating different size of rooms in the building. So the question was that which type of structure is being shown in this image, and it just from what we have learned right now, it is evident that this is double cross wall structure, which is basically a complex system of cross walls set parallel to both the major axes, and it helps in maximizing daylight in the structure as it has been shown in the figure. So the correct answer is double cross wall structure. Moving on to the next question. Ontario's Celebration Zone Pavilion in Toronto is an example of load bearing structure, shell structure, pneumatic structure, or frame structure. First, we will learn about all these kinds of structures. Then we will see how the Ontario celebration zone pavilion looks like, and then we will answer this question. So, load bearing structure, a load bearing structure, in a load bearing structure, the load bearing members are basically walls. So, a load bearing wall or bearing wall is a wall that is an active structural element of a building. That is, it bears the weight of the elements above said wall, resting upon it by conducting its weight to the foundation to a foundation structure. Shell. So basically in load bearing structures there are no columns or beams. The walls are there which take the load of the slab from above, of the roof from above, and it transfers it directly to the foundation, which transfers it to the soils. So that's a load bearing structure. Shell structure. A shell is a thin curved plate structure shaped to transmit applied forces by compressive, tensile and shear stresses that act in the plate of the surface. Pneumatic structure. They are member structures comprising of the volume of inflated air. They are extremely lightweight structures, and existing internal pressure pre-stresses the enveloping membranes and are subjected to tension and counteracts the external loads. Frame structure. In a frame structure, load bearing members are beams and columns, and a frame structure in any material is one that is made stable by a skeleton that is able to stand by itself as a rigid structure without depending on floors or walls to resist deformation. So frame structure is basically a skeleton. It is supposed to be a rigid structure, and it has the ability to withstand completely even if there is no floor or wall. So basically, simplest example of a frame structure would be a beam column structure. It is framed, it is rigid, and it will stand without even any walls or floors, because it is supported. All the load that is happening in a frame structure is going in these load bearing members, which are the columns which are taking the vertical load, and the beams which are taking the horizontal load. So yeah, these are the four kinds of structure. Now coming to the Ontario Celebration Zone Pavilion, this is how it looks like. It is located at the east coast of Lake Ontario, Toronto, Canada. The architects are Hariri Pontarini architects. The area is 1200 meters square. It was built in 2015. The manufacturers are Serge Ferrari, and it was built out of air beams joined by a quilted inflated fabric skin. Two polyester or PVC pneumatic structures are joined together in this. So the question was that Ontario Celebration Zone Pavilion in Toronto is an example of these following structure. And to be able to answer this question, you should be knowing how the Ontario's Celebration Zone Pavilion looks like, and you should also be knowing what all these different kinds of structures are and what they mean and other things. So now looking at this image, it is very evident that it's a pneumatic structure based on air, inflated air. So the correct answer would be pneumatic structure. Moving on to the next question. A massive scaffolding structure mounted on a bridge or platform, supported by a pair of towers which normally run back and forth on parallel tracks, is called breakers, transom, gantry and baseway. First of all these four terms that have been mentioned here are related to scaffolding and shoring. I will just explain what all these four terms are, and then I will explain. Maybe it's a little hard to understand this question if you do not know what it actually is asking. So I will first explain these points, and then I'll come back to the question again. So what are rakers? Rakers are an internal bracing system that transfers forces from the shoring wall to a theoretically more stable zone. So raker, for example, this is your wall. There is a wall plate. So when shoring is happening, we put a raker or this inclined member to help make the structure stable. So this inclined member is called a raker. What's a transom? Transoms are horizontal load-bearing scaffolding components for supporting planks. So this is shoring, and in scaffolding, the horizontal load-bearing scaffolding components are called transoms. Gantry. So gantry is like a bridge-like overhead structure with a platform supporting equipment such as cranes, signals, or cameras. And base plate is mainly used to spread the load onto the sole plates. All uprights or standards of a scaffold are to be mounted on a steel base plate. So the question was, it is first of all asking about a scaffolding structure, so which makes the rakers out of question because it's shoring part, and base plate also is a shoring part. So a massive scaffolding structure mounted on a bridge. So there has what bridge or platform supported by a pair of towers which normally runs back and forth on parallel tracks. So as you can see in this image, you can see two tracks and you can see two bridge towers, and then you can see the structure mounted on the bridge. So this is how is this system works. It is a gantry. So basically it can move. It is supported by it's a fixed thing used for temporary work, and this is how a gantry works, and this is how it looks like. So the question was that it's a massive scaffolding structure mounted on a bridge. As you can see how the structure is mounted on a bridge in the image on the right with the yellow structure, and supported by a pair of towers. You can see two kind of towers, and how this gantry is creating a bridge which normally runs back and forth on parallel tracks, and there are two parallel tracks. This whole structure can move on to be able to help with the another thing which it is being used for. So the answer is of course gantry, and this is how the system of whole gantry works. It's a bridge like structure which also moves, and that's how it works, which has two towers. It is fixed and it also moves. Moving on to the next question. The dash is a system of providing temporary supports to the party walls of the two buildings where the immediate building is to be pulled down and rebuilt. And our options are raking shore, flying shore, dead shore, and underpining. So just a second. Yeah, so we'll first understand what are raking shore, flying shore, dead shore, and underpining to be able to answer this question. Raking shore. So in the raking shore method, the inclined members are known as rakers. They are used to give lateral supports to walls, and rakers are to be inclined to the ground at 45 degree, also vary between 45 degree to 75 degree. So what happens in raking shore is basically the wall is being supported with the raker. That is what is happening in raking shore. Flying shore. So Flying shore, it is a system of providing temporary supports to the party walls of two buildings where the immediate building is to be pulled down and rebuilt, and all the arrangements of supporting the unsafe structure in which the shores do not reach the ground come under this category. So what happens in this is, I do not have two objects. For example, this is the wall of one uh, structure, this is the wall of another structure. So we create some kind of shoring between these two structures to pull down the structure that was in the middle. I'm not able to hold it together, sorry. So, and what happens, all flying shore, everything, every kind of shoring in which the shores do not touch the ground, it comes in this category. They're flying shore, they're in air, they're not touching the ground. That's why it's called flying shore. But the most common case is that there are, this building is there, this building is there, and then this building is there, and these two buildings, the center building is being brought down. So we put some kind of shoring in between so that this building doesn't collapse and this building doesn't collapse. So this is flying shore. It doesn't touch the ground, it just keeps these both structures uh, in position or stable. Meanwhile, the structure that has been fallen down is being rebuilt. What is a dead shore? So dead shore is a system of shoring which is used to render vertical supports to walls, roofs, floors when the lower part of a wall has been removed for the purpose of providing an opening in the wall or to rebuild a defective load-bearing wall. So in dead shore, what happens is that the lower part of the wall itself has to be removed. So it is a shoring in which we give vertical support to the walls. Basically, you support the walls vertically to walls and roofs, etc. And the lower part of the wall is removed and built. So this entire thing is shored so that it doesn't fall down under. Moving to underpining. So underpining is the process of strengthening the foundation of an existing building or other structure. So it may be necessary for a variety of reasons. For example, the original foundation isn't strong or stable enough and the usage of the structure has changed. So what happens in underpining is that you dig out the whole thing and then you support it, you shore it, kind of, and it is not, usually shoring is related to walls, it is to support walls and unstable structures, but underpining, that supports the foundation. So in this, in the you strengthen the foundation of an existing building or other structures in underpining. It is not related to walls, it is about foundation. That's why it is a different term and it is called underpining. So underpinning, not pining, underpinning, it is necessary. So usually the foundation is usually made supported if it's not strong or stable enough, or if the usage of the structure has changed and other reasons. So the right answer would be the flying shore. We would do one more question and then we will take a small break of 5 minutes and then we will rejoin in 5 minutes. So next question is, a series of prismatic trusses linked together form planar truss, space truss, portal frames or space truss. So we understand all four terms. So planar truss, what is a planar truss? So a planar truss is one where all the members and nodes lie within a 2D plane. All the members in 2D plane and none of the members are in 3D plane. If that happens, then it is a planar truss. A space frame is a 3D lattice kind of structure. It is made up from linked pyramids or tetrahedra into a 2-layer or 3-layer triangulated framework. So just like, it's the complete opposite of planar truss. Basically planar truss is a truss in 2D. Not even one member is in 3D, members are in 2D, they're horizontally vertical. And in a space frame, 3D structures are made by making tetrahedrons or then attaching those and then creating a triangulated framework. That's how a space frame is made. Portal frames. So a portal frame uh, building comprises a series of transverse frames braced longitudinally. So, and the primary steelwork consists of columns and rafters which form portal frames and bracing. So, portal frames are usually used when you need a longer span space, and what happens in this is that the transfer frames in this are braced longitudinally. All the transfer frames are braced longitudinally in portal frames. Then space truss. Space trusses are also 3D structures with longitudinal members connected at their ends by hinges assumed to be frictionless. So again our question was that a series of prismatic trusses linked together forms. So the question says prismatic trusses, and as we all know, what is prism? Usually the shape of a prism is a tetrahedron, and the prismatic word is, it is basically saying that different triangles are attached to form a 3D structure and it all are linked together. So coming back to our definitions, where the definition of space frame, it suggests that it's a 3D lattice structure made up with linked pyramids or tetrahedra or prisms, you can say, into a 2-layer or 3-layer triangulated framework. So our correct answer for this question, which asks that a series of prismatic trusses linked together, what does it form? So it forms a space frame. So the answer is B, space frame. And with this, we'll take a 5-minute break and we will restart it in 5 minutes. I will be back in 5 minutes.
We are back. So back to question number 12. Circumferential hoop stress developed in a dome is dash in nature. Is it compressive? Is it tensile? Is it shear? Is it both A and B? So uh, as we discussed in the previous question, that on the meridian of the dome, the forces that occur are compressive forces, and on the hoops or circumferences, the force that occurs are compressive in nature and also tensile in nature. So here they are asking that the circumferential hoop stress. Circumferential means along the circumference of the dome, and they're saying hoop. So hoops are different. If you cut the dome at different levels, you will find hoops. So these hoops, circumferential hoop stress, which are developed in a dome, are what in nature? So we have learned in this previously in the previous question, and I'm again repeating it again. But they are both compressive in nature and they are both tensile in nature, as you can see in the diagram. The dark blue arrows show how the compressive forces are working, and the light blue arrows show how the tensile forces are working. So the correct answer is both A and B, compressive and tensile. Question number 13. Golden Gate Bridge in San Francisco is what? Is it a cable suspender tensile structure, state tensile structure, trussed tensile structure, or a pneumatic tensile structure? So we will learn a little about uh,
So we will learn a little about the Golden Gate Bridge. It is located in San Francisco, Marin County. The total length of the bridge is 2,737 meters. The construction started in 5th January 1933. The architects of this bridge are Joseph Strauss, Charles Alton Ellis, and Irving Morrow. And the clearance below this bridge is 67 meter, and it was opened in 1937, 4 years of construction. The height is total height of the structure is 227 meters. It's one of the longest and highest bridges in the world. I'm not saying the highest, I'm saying one of the highest. So the question was that where does it fall in all four categories mentioned? So we will learn a little about all those categories. So cable suspended tensile structures are basically suspended structures uh, which is supported by cables coming from beams or trusses or columns which sit atop a concrete center column or core. And stage tensile structure, basically what happens in this is that the whole mass of the roof and other things, they are being supported with the stayed cables. The tension members are supported by the compression members, but the major loads are carried out by tensile members. Next is a trussed tensile structure. A truss is a structure that consists of members organized into connected triangles so that the overall assembly behaves as a single object. Trusses are most commonly used in bridges, roofs, and towers. Pneumatic, again, they comprise of volume of inflated air. They're extremely lightweight, existing at under pressure pre-stresses the umbilical membranes and the subjective intention and counteracts the external loads. So the answer is, it is a cable suspended tensile structure, because there is a tower, there are two towers, and then the cables are attached to two of the cables running parallelly through these towers, and the cable is taking all the tension load. So it's a cable suspended tensile structure. Which of the following is not a load bearing structure? Great Pyramid of Egypt, Taj Mahal, not Mahan, Taj Mahal India, Colosseum Rome, La Oceanographic Spain. So I have added the image of all the four buildings: the pyramids, Taj Mahal, Colosseum, and the Oceanographic. And the question is, which one is not a load bearing structure? So as we already know that the Prism, Taj Mahal, and Colosseum, they're all historic structures. They're a part of our history. They have been built way before in time. Pyramids are in fact 3,000 years old, and before the evolution in technology, uh, the structures that were built before the evolution of technology and the invention of concrete and RCC and steel and whatnot. So the structures that were constructed before all that were all load-bearing structures, which means that the walls were taking the load of the entire structure, including the roofs, the walls, the dead load, the live load, everything. So it was being asked which of the following is not a load-bearing structure. La Oceanographic is located in Valencia, Spain, and it's a pretty new structure and it's a beautiful shell structure. La Oceanographic is actually an underwater museum. No, not a museum, it's an aquarium. And there are also parts of this which are underwater aquariums. And it's an amazing building. So the answer would be La Oceanographic, because it is a new structure and it is a shell structure, and the others are very old structures, and at that time with the limited technology they were usually constructing load bearing structures. Question number 15. The vertical member of the tubular scaffold is called standard, ledger, transom, or guardrail. So what is tubular scaffolding first? So tubular scaffolding system consists of galvanized steel pipes that are connected together by couplers and can be erected in virtually any configuration for false work and working scaffolds. So basically it's called tubular scaffolding because steel pipes are being used, which are nothing but tubes. The tubular scaffolding is also known by many names. It is also called steel scaffold, tube and clamp scaffold, tube and coupler scaffold, tube and fitting scaffold, and others. I have added one figure here which is basically showing um, all the different parts of a tubular scaffolding system. So if you can see on the image, you can very clearly see that um, the transom or the put log is the horizontal member. The ledger is another member that is supporting the vertical and horizontal joints. And you can see the vertical member, it is usually called a standard, and there are other members that have been shown here. So very clearly from this diagram, if you see the different parts, you can understand that the vertical member is called a standard, the horizontal member is called transom, and the member that is at the joints of horizontal and vertical member is called a ledger. So these are different parts of tubular scaffolding in which galvanized steel pipes are used. So our correct answer would be standard. So next is barrel vault is basically a under dash. So is it a twister structure? Is it a geodesic dome? Is it a tensile structure or is it a compressive structure? So we will learn a little about barrel vault to be able to answer this. So what is a barrel vault? It is also known as tunnel vault, wagon head vault, and it is basically an architectural element formed by the extrusion of a single curve along a given distance. The curves are typically circular in shape, lending a semi-cylindrical appearance to the total design. A barrel vault is effectively a series of arches placed one after the another to create a tunnel, and barrel vaults were not exclusive to the Romans and were utilized by the ancient Egyptians and the Etruscans. And some of the compression only structures are familiar form of walls, arches, shells, grid shells, and vaults. So is it a twisted structure? No. Is it a dome? No, it's a vault. Is it a tensile structure? No, it is not tensile structure because no pulling load is occurring over here. Is it a compressive structure? Yes, because it is taking all the load in the form of compression and transferring it to the ground. So it is a compressive structure. Which of the following is an example of anticlastic tensile structure? This is our last question of the evening. So the four options are Renault Center, Swindon, UK, Tokyo Dome, Clifton Suspension Bridge in Bristol, Gallery of Skysong at Arizona State University. What is basically an anticlastic tensile structure? So they are tensile surfaces which carry only tension and no compression or bending. They rely on double curvature for their stability, and the stability is provided by the opposition of two curvatures which enable the surface to be tensioned without losing the form. The tensioning of the surface reduces its elasticity, and so the tendency to deform under load, and the curvature itself means that the surface will deform less for any given extension. Anticlastic surfaces are those in which the centers of curvatures are located on opposite sides of the surface, and it is commonly described as a saddle shape, which you can see in the figure that I have added. So what it is saying basically as the there is this curvature, there is this curvature, and there is this curvature, and it is saying that the center of these curvatures are on the opposite sides of the surface, are on the opposite side of the surface. So this is what an anticlastic surface is. And the question that was asked was that which one of the following is an example of anticlastic tensile structure, and the four options. So the four options, I have added image of all the four options here: Reynolds Center, Swindon; Tokyo Dome; Clifton Suspension Bridge in Bristol; and the Gallery of Kaesong at the Arizona University. So it is very evident that the Tokyo Dome is a pneumatic structure, and the Clifton Suspension Bridge, it is already in the name, it is a suspension bridge kind of structure. And as you can see at Gallery of Sky Song located at the Arizona State University, you can see the structure is actually having different kind of curvatures which are in different directions. And as explained here in the anticlastic structures, so our correct answer would be the Gallery of Sky Song. And this was the last question for today. We did 17 questions today, and I would start the Q&A doubts if anybody has to ask anything. If anyone has any questions, they can write their questions in the chat box, and I would try to answer them as well as possible as per my capacity and my knowledge. And if I'm not able to provide you an immediate answer right now, I would provide the answer in the next live session after researching or reading on the asked question or the topic. We would stay in the call for 10-15 minutes in case anyone wants to ask any question. If nobody wants to ask any question, we will end the meeting. If anyone has any doubts, you can ask your questions. You can type the question in the chat box. I would try to answer your question. From today's lecture, week 4, if I'm not able to answer your question, I would definitely answer your question in the next live session after researching on the topic. So if anyone has any doubts, you can please put it in the chat box. We'll wait in the meeting for 10 minutes if anyone has any questions. Since nobody is left in the meeting, we would conclude the session. And end the meeting.